Welcome back to the third part, where we are now looking at advanced features with Storm, and in particular with Stormpy. So Stormpy are the Python bindings for Storm, and because Python is a little bit more user-friendly, it allows an easy access to Storm's algorithms and features. At the same time, because we're calling the algorithms and features within Storm, it maintains the performance of Storm. That means we can profit from the fast performance of Storm within our favorite programming language, Python. And as the effect, these Python bindings allow for rapid prototyping. That means we can implement our own customized approach based on probabilistic model checking. And we will look into that now in detail. You can, of course, also find more information at our webpage at stormchecker.org/stormpy. So now we're looking at Python and Python code. That means in the following everything is written in Python, and we start by just running Stormpy. We need to import the library Stormpy, and then we can output some general information about the version of Stormpy we're using, for example, just to check that everything is set up correctly. So in our case, we're using Stormpy version 1.6, and we're using Storm also in the same version. As our running example, we're now looking at an MP3 player. We have a rather simple MP3 player, which can contain 100 songs. And we start at a random song. And our goal is we want to listen to our favorite song, which is song number 42. The problem is we only have two buttons at our MP3 player. We have the next song button, which, as the name states, goes to the next song in increasing order. And we have the random song, which leads us to a random song. And now our question is, we want to find our song number 42 with the fewest amount of steps necessary, so the fewest button presses. And the question is, what is the expected number of button presses we need to do to reach our song? And more importantly, which buttons should we actually press in which order? And we use probabilistic model checking to try to solve this problem. So as before, we encoded our Markov chain in a Prism file, which is called music shuffle. And we start by just parsing this Prism program. And after we parsed it, we can get some general information about that. For example, here we can see that it is of type MDP. That means we again have a Markov decision process. Next, we have to build our model. So we set some options to build some more information. But in general, we basically say we want to build a sparse model from our Prism program, and then we get our model as a result. And now for this model, we can output some information. So for example, we can output the number of states, which is 101. We can also output the number of transitions, which is over 10,000. And we can output some of the labels we have in our model, which we can later use for our properties. So for example, here we have an initial label for the initial state, and we have, for example, the found label, which indicates now we have reached our favorite song number 42. So after we have now the model, we can follow the same approach as before with Storm to model check our model. And that means we have to set the second input, the property. In our case, we set it like this. So we set what is the minimum expected number of steps which we need to finally reach our label found. So what is the minimal expected number of steps to reach song number 42? We input this as a string, and then we use Stormpy to pass this as an actual property as a data structure Storm understands. And then we can just do the model checking where we give the model and the property, and then Storm does automatically the model checking, and then we get the result out of that. And then we can output the result at the initial state, and then we can see the expected number of steps to reach our song is a little bit over 12 steps. So far, so good. That is basically the same approach as we would have done with Storm. So basically we pass our file, we prepare our property, and then we use both of them to model check. So basically this is the same as in the command line interface, but as we are now having a Python interface, we can of course do more. And one of the first things we can do is to explore the model. In our in Storm, usually you saw you only got the number of states and that was it. But here now we can get some more information. So what we do now is we pick out the state number 2, in our case here, and then we print some general information about the state. For example, what kind of values do the variables have in the state. So for example, we can see here now in state 2, we have a variable initial, which indicates it has been initialized. And we say the variable current, which basically represents the current song, means we are currently at song number 1. So that is our state, and then we can see what kind of possibilities do we have from this state. And that means we iterate over all the possible actions in this state. And for all actions, we iterate over all the probabilities, over all the transitions which belong to this action. And then we can output them here, and we see we have one action next, where with probability 1, we go to the state 3, and we can see that this is represented by the current position at song number 2. That means from song number 1, with the next button, we go to song number 2. That's the one choice we have. And the other choice or action which we have is the shuffle action, which represents the random button. And then we have a certain probability of 1 over 100 to go to state 1, basically the first song. And we have a probability 1 over 100 to go to song number 1 and to song number 2 and so forth. So here now we can explore our model in detail and see if it is actually the model we would have expected. Afterwards, we can also look at our result a little bit more into detail. So we only got the result for the initial state, but it might be interesting to see how does the result to reach song number 42 differ from which song we actually start from. So what we do is we plot it. We use the Python library matplotlib for that. And the part above here is just to set up all the plot. And then what we are doing here is basically the important part. From our model checking result, we get the values for all the states and we plot them. And this looks as follows. So here on the x-axis, we have the current song number from 0 to 100. And then we have on the y-axis, we have the expected steps till we reach song 42. And then we can see here for the red line is indicating song number 42. We see that the expected number of steps is 0 because we have reached it. And then we can see for all of these songs which are a little bit before 42, we have a decreasing number of steps because we basically get nearer to the song we want to reach. And we can see here, interestingly, at song number 28, that is the point where it starts to decrease. So there might be something important going on at song number 28. And for all of the other songs, so below 28 and above 42, we basically have the same expected number of steps, which is a little bit over 13. So let's look at the solution a little bit into more detail, and most importantly, answer the question, which button should be pressed at which point? Because now we know what the minimal number of steps is, but we also want to know what strategy do we have to do, what kind of buttons do we have to press. And the solution is we use a scheduler which determines the optimal choices for each of the states. And we do that again by model checking our result. We input again model and property, and what is important now, we set a flag which says, okay, we're also interested in the scheduler, so please generate the scheduler as well. And then we get the scheduler from the result, and we can assert that it is memoryless and deterministic. That means at each state we have exactly one choice or one button which we have to press. And then for each of these states we can get this button from the scheduler getting the choice for each state, and that we can, because it's a deterministic choice, we can get the action from that. And then we can fill it, and then we get a dictionary of all the buttons we have to press, which looks like this. But of course this is not nice, so let's again do it as a plot. So what we can see now here is again the current song number, and on the y-axis we have two possibilities. We have the next button and we have the shuffle button. And now we can see that for a lot of cases, we basically press the shuffle button and hope for a better position. But if we are here at, which is song number 28, we start pressing the next button. And as we saw before, that decreases the expected number of steps. So at song number 28, we are near enough to the actual song 42. At this point, we start pressing the next button, and for all other songs, we basically hit the random button and hope to land in this good interval. Now, this was one objective which we had, which was basically trying to reach song number 42. But in reality, you might have more than one objective. So for example, here we have two objectives. We want to reach song number 42, and now we want to reach it within the first 10 steps we make. So within the first 10 button presses. But at the same time, there are some songs, in particular songs 1 to 10, which are not our favorite ones, and we want to avoid listening to them. So we want to avoid listening to these songs before we listen to song number 42. And this is also restricted to the first 10 steps. So we now have two objectives. So we have multi-objective model checking. And these two objectives compete a little bit. So we want to find the best trade-off. And we can see that now. If we put it into Storm again, now we have it in our command line interface again, and the property here is a multi-objective property, and we list both of the properties. So the first property is we want to maximize the probability that within 10 steps we reach our favorite song. On the same hand, we want to minimize the probability that within 10 steps we reach one of the avoid states while not finding our favorite song. So this is now an until formula. So we have now these two competing objectives, and we can model check it and display the corresponding plot. And now what we can see here is on the x-axis we see the probability that we find song number 42 within 10 steps, and on the y-axis we see the probability that we avoid one of our songs, that we encounter one of our songs within the first 10 steps. That means the farther to the right we are here, the better for us, and the lower we are here, the better for us, because we have a minimal probability of reaching one of the songs we want to avoid. Everything which is red is not possible, and everything which is green is possible with some strategy. And now we can see the trade-offs. For example, if we go here, this is a high probability that we find our song. So for a little bit over 40% chance to find our song within the first 10 steps. But on the other hand, it's a very high probability also, like 70%, that we reach one of the songs we do not want to listen to, also in the first 10 steps. On the other hand, here, for example, below, we have a quite low probability to reach one of our not favorite songs. But on the same hand, if we are here, it's also quite low probability to actually reach our song 42. So depending on the trade-off, all of these points here are optimal on this Pareto curve. But depending on the trade-off we have then to select which points we are actually the best for our objective, given how much we prioritize which objective. So this is one of the possibilities which is possible with Storm and Stormpy. Another possibility is to do parametric model checking. So that means instead of having concrete probabilities, we leave some of the probabilities open and use parameters instead. So for example, if you do not know exact probabilities, like for example, how likely it is that a certain component fails, you can leave it open with certain parameters and then try to figure out how good the reliability is, even if it's the worst case of the failure probabilities. On the other hand, you can leave the probabilities open because you want to synthesize optimal probabilities. And that's what we're doing in our second case here. We have now the music shuffle in the second version. And here we have a smaller MP3 player. We have only 20 songs. And we start always at song number 10, so in the middle. But now it's a simpler MP3 player. We only have one button anymore. That means this is a probabilistic button. That means with probability P, we go to the next song. And with probability 1 minus P, we go back 2 songs. So that means the higher the probability of P, the more likely it is that we go forward 1 song, and the lower we go back 2 songs. And now our objective is to listen to song number 12. And we can actually compute this now with Stormpy. So it's the same structure as before. We first pass our program, we pass our properties, which did not change. The thing which changes here is that we build a parametric model now. And then we do the model checking again, and we can print the result. And the result looks like this. This is a rational function in the parameter p. That means depending on the probability p, we get different probabilities. And as we can see already for such a small example, the rational function can get quite complex. And that's why we want to, of course, plot it again. So let's plot it. And now on the x-axis, we see the value of our parameter p. So the farther to the right, the more likely it is that we go to the next song. And the farther to the left, the more likely it is that we go back to songs. And then on the y-axis, we have the expected number of steps till we reach song 12. And then we can see we want to minimize this expected number of steps. And as we can see, the best value would be here to have something deterministic, which you might have guessed before, that if we just press the button 2 times and we are deterministically choosing the next button, then we are reaching song number 12. But of course, this only works because we want to reach a song which is a little bit above our starting position. If we want to reach different songs, the picture might look quite different. So now we have here the expected steps till reaching song number 12, and here we have the expected steps till reaching song number 3. And then we can see, for example, the best value here would be something in the complete opposite direction, because we want, of course, to go back. But at the same hand, if we choose something here, we can see that reaching song number 12, of course, has a very, very high number of steps. So we have to find a trade-off here and find optimal values, which might, for example, optimize both properties here. So this was a short introduction to Stormpy and more of the advanced features you can do. So Stormpy, as said, are the Python bindings for Storm, and they allow an easy and rapid access to the features of Storm. So instead of having to dig through the command line, they allow you to basically chain all the commands in the right way, and then you can get what exactly you want. That means it allows for user-guided analysis. So you can pass a model, you can build the model, and then you can explore the model like we did before to see what kind of states do I have, does the model actually correspond to what I was expecting. And then instead of just getting a number out of it for the model checking result, you can, for example, guide the analysis and get schedulers, which give you more information, or you get results for all the states and so forth. So it helps you in getting the right analysis for your purposes. And the other benefit is because it has access to all the features of Storm, you can fast prototype new tools and approaches by just combining the features of Storm in Python, and then you can develop your own tools and approaches based on probabilistic model checking. So to conclude this tutorial on Storm, Storm is efficient as seen in the QCOM competition. It has a modular approach for solvers, which makes it easy to exchange solvers and develop new solvers, and then a lot of internal algorithms profit from these new solvers. It has specialized engines, which means depending on the model and the property, you can choose the correct engine which gives you the best performance. Storm also supports a broad range of properties, so you're not restricted to only computing probabilities, but you can also compute expected rewards, you can compute multi-objective properties, you can compute conditional probabilities, and so forth. It also offers you the possibility to do parametric analysis, where you leave some of the probabilities open. It gives you the possibility to do exact model checking, as we saw in the part 2. And of course, there are many, many more features which we do not have time to talk about. So for example, partially observable MDPs, where you only have a certain probability that you're in a state, so you don't fully observe in which state you are. We have generalized stochastic Petri nets, which are an extension of usual Petri nets with time transitions. We have dynamic fault trees, which are a model in reliability engineering, which model how failures propagate in the system, and many more. So in conclusion, we encourage you to try out Storm. Visit stormchecker.org to try it out, or just play around with this presentation. And if you have any questions, feel free to ask them now or later by writing us an email. And that concludes it. Thank you for your attention.